¿De qué nos va a hablar? De el universo. Empecemos por lo pequeño que somos y lo enorme e inmensos que somos. Bienvenidos, welcome, thank you, bienvenidos.
The question mark in this title is very important, and it's not simply a reflection of what's been going on in the last 18 months north of the border. It is, in fact, a profound question about what we mean by intelligent life in the universe, and I'll come back to that at the end. It's been a question, however, that's as old as humanity. What is our place in the universe? In what chapter of the universe's history do we appear? You live in a unique moment in the 4.5 billion year history of this planet, in that we now know the answer to that question with a precision unimaginable even 20 years ago. My cosmology professor, Ted Harrison, divided human thought about the universe and our place in it into three broad categories: the anthropomorphic, the anthropocentric, and the anthropometric. The anthropomorphic universe is what we imagine prehistory to be like. It's an age of magic. It's when there's no division between ourselves and our emotions and things that go on in the natural world. Some of this still persists in our speech. We speak about angry storms and gentle breezes as though they had the same kind of emotional underpinning as our own lives do. We say this is what prehistory was like, but of course this still exists in many university English departments, and also in Southern California. The anthropocentric universe is the age of myth. It saw the creation of this pantheon of powerful gods. But these gods, which control all natural phenomena, were driven by human emotions and obsessed by human concerns. It is in a very fundamental sense a geocentric or Earth-centered universe, and it's the universe, in fact, in which most people still reside today. The anthropometric universe is the age of science. It's that man not is the measure of all things, as Protagoras would have it, but that one can take the measure, that there exists an external, objective, material world, and that we can use the 100 billion neurons up here to assess that quantitatively, build models of how it works, and make predictions. This age began, of course, about 400 years ago with Galileo. Galileo first resolved the stars, resolved the Milky Way into thousands of stars. The first telescope in 1610 saw this band of light across the sky, of which myths had been made up for all of human existence, with actually lots and lots of individual stars, thousands of them, more than could be imagined. And Galileo speculated that these, in fact, were other suns, like our sun. He was correct in that speculation, and that they might have retinue of planets around them the way our sun did as well. It took nearly 400 years to find out whether that was true. What we're going to do in the next 40 minutes or so is to calculate the number of intelligent communicating civilizations there are in our galaxy, the Milky Way. And that means we're going to write down an equation. Now, there's only one equation, so don't get nervous. And that equation, N, is going to be the number of intelligent communicating civilizations currently existing in our Milky Way galaxy. And this is the equation. Don't get scared. But we're going to take them one at a time, and it really won't be painful at all. So, let's take them one at a time. What is R? R is the rate at which stars form in our galaxy. Now, if you go out at night outside the city here, you see the sky just littered with stars. You might think there's a million stars, but in fact, with your naked eye, you can only see about 2,000 stars at any one time. But if you recorded very carefully the positions of those stars, the relative brightness of those stars, and if you're in a very dark place, you can see some are tinted a little bit to the blue and some are a little bit to the red. And you came back the next night, you see exactly the same stars, in exactly the same locations, with exactly the same relative brightnesses, and exactly the same colors. And if you came back 50 years hence, it's going to be pushing it for some of you, I think, but anyway, then you would see exactly the same stars with the same colors and the same positions and the same magnitudes. And this gives you the false impression that the universe is this placid, unchanging place where nothing ever happens. But in fact, stars are born, they live out their lives, they have a relatively boring middle age, and then they die. And the life cycle is much better understood than the human life cycle. If you tell me the mass of a star, I can tell you to within a fraction of 1% exactly how long it would live, which fortunately I guess I can't do for myself. So, stars are born, and what we need to know is the rate at which stars are born in the galaxy, because they're going to be the hosts for our planets that host life. Stars are born in giant clouds of gas and dust. These are all true color, actual pictures of the Milky Way taken with the Hubble Space Telescope. These dark regions here don't represent an absence of material. They represent the densest regions. Interstellar space is full of dust, sort of filthy, and as the gas and dust collapse to form a new generation of stars, it gets so dark you can't see through it. Here you see a huge dark cloud, inside of which there are dozens of stars today in the process of formation. You can see this in these beautiful pillars of dark clouds of gas and dust. Now, with our visible light that our eyes can see, and the Hubble Space Telescope can see, we can't see through this dust. It's black. But what we've been doing over the last 75 years in astronomy is opening new windows on different parts of the spectrum that our eyes and our basic telescopes aren't equipped to see. We can peer through this dust with infrared cameras and infrared telescopes, and this is what it looks like. You can see there's all those yellow stars there, which didn't appear in the other picture. Those are stars forming out of the collapsing clouds of gas and dust, which make up these pictures. So we know that number now, because we made a census of the galaxy, and the answer is 2. Not very surprising, I guess. 2 stars a year. Now, when our galaxy formed, it was much more gas and many fewer stars, and it was maybe forming 100 stars, maybe even a few hundred stars per year. But the galaxy has been around for 11 billion years. And over 11 billion years, most of the gas is turned into stars. So now it's 90% stars and 10% gas, and we're really running out of fuel, so we're only forming about 2 stars per year. And we know that number quite precisely now because there are a number of different ways we can measure it. So there's the first term in our equation. The next one, Fs, is the fraction of those stars that are suitable to host planets that could, in principle, harbor life. Now, you might say, how can you tell what suitable is? Because you don't know what this other life will look like. But there's some basic chemistry and physics that applies not just on Earth, but applies throughout the universe. And we know, for example, that such stars need heavy elements. Life, if it's going to be complex enough to communicate, needs many elements beyond hydrogen and helium, which is all that existed when the universe and the galaxy formed. So we can't look at the first generation of stars, which was only made of hydrogen and helium. We have to look at the second, third, fourth, and fifth generation of stars, which had enriched material to form from that had heavy elements as well. And that eliminates about 20% of the stars in our galaxy. Furthermore, we need a long time for life to develop, and we don't want any high-energy radiation from these stars, because high-energy radiation breaks apart complex molecules. It turns out those are the same set of stars, the ones that are much more massive than the sun, so that eliminates another 2%. And finally, we need stable orbits. Our sun is a very typical star in many senses, average age, average size, average mass, but it doesn't have a companion. Most stars have a companion, sometimes 2 or 3. And if they have a companion orbiting around each other, planets get confused, and they might get kicked out of the system and wouldn't have a stable place for life to evolve. And so that eliminates another few percent, maybe 10% of stars. So this number, Fs, is about 70%. About 70% of the stars that exist in our galaxy and being formed today are appropriate to host planets. What about Ft? That's the fraction of stars that host planets. Here's where we've made the most progress in the last 20 years. 23 years ago, we knew of no planets other than the 8 planets in our solar system. We didn't know if a single other star had ever formed with a planet around it. And now, fortunately, we do. We knew stars formed in these dense regions, and we knew that as these regions collapsed, they tended to collapse into pancakes that look like this. These are a few times the size of the solar system, but they're very thin. There's a star in the middle there that you can't see, and a disk of material surrounding it. Here's another example of one that's further along. The star is buried in here. It's got a disk of material around it and shooting jets out the North and South Pole. When we look deep into these star formation regions, we see that the newly forming stars often have little black disks of material around them. They're a couple times the size of the solar system, and they contain just about enough matter to make up planets. Right, but this is just circumstantial evidence. Until this telescope is dedicated. This telescope is in the Atacama Desert in Chile at 5,100 meters. Probably didn't know there was any flat place that was that high. But it's 18-kilometer plane over which we've arrayed 66 telescopes, each of which is 12 meters in diameter, so a human couldn't easily see in this picture. And we managed to combine the signals from all of those telescopes through optical fibers to make a single telescope 18 kilometers across, which gives us a view that we couldn't possibly get any other way. And this is what we see. We see the newly forming star in the center, and then we see these racetracks around here, empty of material. Another one there, another one there, another one there, which we imagine are solar systems in formation. We imagine these little rocky bodies that are forming there, and they're sweeping up all the gas as they orbit the sun, the new sun in circular orbits like this. Here's another spectacular example where we're looking directly down on this disk of material. You see the sun right in the center. You see one planet forming there, another planet forming here. This one is exactly the distance of the Earth from the sun. So we're now getting to see these in formation, but we still haven't seen the planet. We want to know if these planets really exist. This is still sort of circumstantial evidence. So how can we do that? Well, it turns out that it's not so easy. For example, let me give you a sense of the scale of things by using my props. So the sun is 1.5 million kilometers in diameter, but it's yellow and it's round, and so we're going to shrink it to be the size of a tennis ball. Okay, so this is my sun. We're going to put the sun over here, and if that's the sun, then the Earth represents this tiny pebble, which you can't even see, and which is located about this far away. So could you hold the Earth for the rest of the talk? And the other planets are in the back of the auditorium, and one of them, Neptune, is out in the front of the building. And then the next star is very similar to the sun, so it's another tennis ball, same size, same color, in Los Angeles. And there's nothing in between. And the one in Los Angeles has a little grain of sand orbiting as well. And so the problem of finding planets around other stars is sitting on my grain of sand in his hand and finding the grain of sand orbiting the tennis ball in Los Angeles. It's not easy. But technology advances. And now we have several ways of doing this. First of all, how do planets move? Well, textbook pictures show you the sun sitting in the middle and the planets going around like this. But of course, as the sun attracts the planets attract the sun. So in fact, that's not the case. They both orbit their center of mass. And so a planet orbiting a star looks like this, where the planet makes a big loop around the star, but the star simultaneously is moving slightly towards and slightly away from you as the planet moves away and towards you. See that motion? And that means that we can detect the motion of the star. If something emits a signal and it's standing still between two stationary observers, you both see the same thing. But you all know that if you've been standing by the side of a highway and you hear trucks going by, they sound like this. That's because as it's coming towards you, the waves are pushed together And as it's coming away from you, the waves are stretched apart. So you hear a high pitch and then a low pitch, like this. The girl on the right sees the waves close together, that's the high pitch, and then the guy on the other side sees it moving away. So it means a star that moves towards you and away from you changes the pitch, or in what we see, the color of the light as the planet orbits it. So here we have the unseen planet moving away at the top. That means the star is moving towards you at the bottom, which means its light is shifted slightly towards the blue. And on the bottom, the planet is moving towards you, so the sun is moving away, and that means it's shifted slightly towards the red. Now, it's not nearly dramatic as I've illustrated in this picture. It's a very, very tiny shift, but we've learned to measure that shift, and therefore we can measure the speed. And in November of 1995, we detected our first planet around another star, moving first towards us, going down the slope, and then away from us, and then towards us, and then away from us, in a regular motion, indicating that an unseen planet was orbiting the star. Yeah. We've now done this for thousands of stars, and we've measured planets of masses ranging from smaller than the Earth to masses that are larger than Jupiter. Another technique, if you happen to be sitting in exactly the right place, and of course we don't get a choice, we're sitting on the Earth, but if there's a sun here and a planet moving across right in front of it, the planet will block the light from the star. And as a consequence, well, you can't see these two things. Remember, it's a grain of sand in Los Angeles. But you can see the light from the star dip a little bit. As the star moves across, it's going to block some of the light of the star, and as it moves out the other side, the star will recover. And here's some real data, where you see the star was shining steadily, and then a planet eclipsed it, and then the planet moved across the other side. And this allows us to measure the size of the planet. The other technique allows us to measure the mass of the planet. When we can do both, measure the size and the mass, we can measure the density of the planet, so we can figure out what the planet is made of. And in the first 10 years, by using these two techniques, plus a couple of others I don't have time to describe for you, in fact, we found 156 other planetary systems. So Galileo was right to speculate that these stars were other suns and that they had planets like our own. We went from a state of knowledge where the planets in our solar system were the only ones we knew of, to a state where we find that planets are common around other stars. And then we launched a satellite, and the rate of discovery took off, such that now there's planets all over the place. Thousands and thousands of planets. Now what does this graph show? This shows the planet's size, or the radius of the planet, okay, on this axis here. So that's the size of the Earth. That's 4 times the size of the Earth. About the size of Neptune. That's 10 times the size of the Earth. That's about the size of Jupiter. And on the bottom axis, which seems to be cut off here, we have the orbital period, how long it takes to go around, how long 1 year is on that planet. And in fact, this is 365 days, and this is the size of the Earth. So that planet there is an exact analog of the Earth. You see there are a bunch of other planets at roughly the same period, and some even longer. These guys are big planets like Jupiter, probably made of gas. These planets in here don't exist in our solar system. In our solar system, the Earth is the biggest rocky planet. Venus, Mercury, and Mars are down here. And Neptune is the smallest gaseous planet. All these planets are completely unknown to us. Are they made of rocks? Are they made of iron? Are they made of water? We don't know. We can sort of roughly divide these up. We get the big gaseous planets close to their parent star. We call those hot Jupiters because they're like Jupiter and they're hot because they're close to their parent star. And then we have big cold gas giants that are also like Jupiter but far from their parent star. We have ones in the middle that are Neptune size and a little smaller, which could be made of gas like Neptune, but could also have icy moons like Neptune, Uranus, and Saturn have. And they could also be made of water, because water is one of the most common elements in the universe. Then we have down here the rocky planets. You see there's thousands, literally thousands of planets that we think are like Earth. And the ones that are extremely close to their parent star, so they orbit every day or so, are suddenly so hot they're probably lava-like, and they look like what Hawaii looks like now. But these are all very interesting, and these can all have moons that harbor life. So, we've gone from a situation any planets to a situation where there are 3,000 800 and some confirmed planets and more than 5,000 new candidates. And maybe if you're in the front row, you can barely see this. This is all the stars, 4,696 of them as of July 2015, with those little tiny black dots crossing each of those stars representing the planets. Sometimes 1, sometimes 2, sometimes 5, sometimes 7. The biggest solar system we've discovered so far has 7 new planets in it. So, what does that tell us? We finally got another term in our equation. By calculating all the stars we've observed, by carefully taking into account which planets are easy to detect and which ones are hard, what we managed to do is calculate the fraction of suitable stars, only the suitable stars that have planets. And the answer is about a third, about 35%. And, therefore, we're almost done with the astronomical parts of this equation, because the next term is how many of these planets have a suitable environment. Now again, who's for me to say whether the environment is suitable or not? Well, I can do that because of the unity of Earth and space. The 92 kinds of atoms we have on Earth are identical. And when I say identical, I mean their properties are identical to 8 decimal places. We've measured them to the atoms that exist across the universe. Everything's made of the same stuff. Furthermore, the chemistry that links those atoms together into molecules that can store information and ultimately become life is identical across the universe. We can measure this directly. The physics of gravity and the other forces involved, the energy and the light that are sent our way, are all identical. So while I can't say whether these alien creatures are going to have 2 eyes or 4 eyes or any eyes at all, what I can say is that with a very primitive definition of what life is, whether life could exist on one of these planets. And here's my definition of life. A self-reproducing chemical information system capable of Darwinian evolution. Now this may not sound like your mother-in-law, or it may sound like your mother-in-law. Anyway, the point is that those are the sort of basic elements of life. It's got to be self-reproducing. Crystals have elegant structures, but they don't self-reproduce, and we don't call them alive. But bacteria do, and we do call them alive. So self-reproducing is critical. Chemical information system. There are conceivably other ways to store information. The famous science fiction novel by Fred Hoyle called The Black Cloud had a black cloud that was intelligent and stored information with magnetic fields. So we're going to imagine going beyond this, but let's just try to be conservative here and say that our information system is going to be made up of basic chemistry that we understand. And capable of Darwinian evolution, we don't ever expect molecules to happen to come together to form an intelligent, technologically literate individual out of a sea of unrelated molecules. We expect primitive things to form first and then to evolve over a long period of cosmic time. And so that's why Darwinian evolution is important. Not that we use DNA and RNA, the molecules will undoubtedly look different than that. But rather that there is a code that passes things from generation to generation, and that code can have variation, and the environment in which those organisms are evolving will adapt to the environments in which they're evolving. So we can say what a good range of temperatures is, and we can say what a good range of elemental compositions are, because we need a set of atoms to make complex molecules. So we don't just need hydrogen and helium. We need carbon and nitrogen and oxygen and sulfur and silicon and argon and iron and other elements like that. Furthermore, we can set a limit on the temperature. And we can do this because temperature is just a measure, you may not have thought of it this way, but temperature is just a measure of the average speed with which molecules are moving around. The temperature in this room is 20 degrees C because the atoms in the room, in the air in the room, are moving around at about 450 meters per second. Half a kilometer per second. Zing, 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 all over the place. If we turn on the air conditioner and made it cooler in here, that would just mean the atoms are moving slowly. We just slow down all the atoms. That you experience as cool. If we turn the heat on, you make all the atoms move faster, that's what we experience as hot. So temperature is just a measure of the speed with which molecules move. Now, since chemistry is the same anywhere, if you have 2 molecules, and they're moving so slowly that they'll just never encounter each other, then that's probably not going to be a good place to build up intelligent life. On the other hand, if we have 2 molecules that are moving so fast that every time they collide with each other, they break apart, That's not going to be a way to build up a complex system of information storage through chemistry. And so we can set a limit on the range of temperatures that is plausible for any complex molecule to form, both that it's moving fast enough to form in some reasonable time period, and it's moving slow enough so it doesn't collide and fall apart. And as a consequence, then, we can plot a diagram like this. Sorry if it just fell off the edge. This is mass over here of the star that's hosting it, and these are all the potential planets. And what it says on the bottom is the amount of radiation that these planets receive compared to what our planet receives from the sun, which of course is a nice temperature from us. These are all receiving more energy, so they're probably too hot. Molecules there will fall apart. These are very cold. They're not receiving very much energy, and so molecules won't stick together. But over here, you see there's about 100 dots in there, are planets that are receiving the amount of energy from the sun that we would expect to lead to an environment conducive for the creation of complex molecules and the lack of their destruction. Now, of course, the Earth's atmosphere plays an important role in modulating our temperature. And so, in fact, some of these hotter ones could actually be cool enough with the appropriate kind of cloudy atmosphere to support life. And some of these cooler ones, like Mars would be over here right now, in the past might have thicker atmospheres which allowed them to be warm as well. So this again is a very conservative fraction here of the number of planets that are in the right environmental zone. And so I put my last term into the equation that we know of from astronomy, and that is roughly 30% of the solar systems that we're finding, just exploring our little local region of the galaxies, are going to be in a zone that are habitable for intelligent life. And so what does that mean? That means the astronomy tells us that we form two stars per year, that 70% of all the stars in the galaxy are suitable hosts for planets, that 35% of those stars have planets of a reasonable size, mass, and distance, and that 30% of those are in a suitable environmental zone, meaning that if I multiply those terms together, the astronomy tells us there are 0.15 solar suitable planets in suitable environments around suitable stars born in the galaxy every year. That's one every 7 years. Doesn't make us sound very special when you realize the galaxy is 10 billion years old. So every 7 years, there's a planet forming around a star in our galaxy that in principle could host life. Now, we come to the biology part. That's a lot harder. The fraction of stars and planets on which life evolves, the fraction of that life that becomes intelligent, and the fraction of the intelligent ones that decide to communicate. So I don't know those numbers, because I so far have one example, and you can't choose statistics with an example of one. But I can set limits, because we're here. And again, ignoring the last 18 months north of the border, we can say we're an intelligent species. And so, well, this is going to be a problem. Is there any way you can shrink these slides? Because all my information is from the top and the bottom of the slides. Well, what it says is that since we know we exist, we can set n equal to 1. And furthermore, we've been able to communicate with another equally advanced civilization over vast interstellar distances for 50 years. We've had the technology to do it over 50 years. And if we can do that over 50 years, then one civilization times my 0.15 times all those things about life times 50 years tells us that the biology has about a 7.5% chance of happening if we're the only intelligent species in the galaxy. That is 7% of suitable planets develop like us if intelligent life only lives for 50 years. And again, unfortunately, we have some evidence that that may be true. Now, suppose, however, we're more optimistic about the future of our planet. And suppose we say that there's one planet in our galaxy with intelligent life, and we've got the astronomical factor of 0.15, and we've got the biological factors in yellow, and we multiply by the average lifetime of a species on our planet. We know this from the fossil record. How long does it take for species to come into existence and then go extinct? And the answer is about 6 million years. So, So, if we put in 6 million years for the lifetime of intelligent civilization, then the biological factors say it's only 1 in a million. Only 1 in a million planets in our galaxy develops life, intelligence, and communication ability, if we are alone. So, are we alone? Well, what's the rest of the circumstantial evidence? When we peer down with that telescope in Chile into the regions where stars were forming today, this is what we see in the radio spectrum. We see all the same organic molecules that we find on Earth that are the precursors for life. There's nothing special about the chemistry of where we live. In every one of the clouds of gas and dust, where new stars and new planets are forming, we find all the raw ingredients necessary to produce life. And furthermore, when we look around the Earth, we find fossils from when the Earth was only about 500 or 600 million years old. The Earth is now 4.56 billion years old. And life formed really quickly. In fact, it formed so quickly and spread so widely that we now see these huge fossils. These are called stromatolites. They're in Australia. You see these huge fossils left over from mats of algae that were already dominating the Earth in only 7% of the lifetime of our sun. So what do we know about life forming in the universe? Well, we only have one example so far, but we know that the raw materials are everywhere planets form. And we know that in our case, it happened really quickly in terms of the lifetime of the star. So, what does that tell us? The number of intelligent communicating civilizations in the galaxy depends on 3 things. The astronomy, we nailed it. When this equation was written down in 1960, we didn't know any of those 4 terms. And in my lifetime, all of those have now been determined. It's about 0.15 habitable planets per year. Biology, we have just one example. But we know that the raw materials are always there, and it happened really fast. The sociology is, to me, the most uncertain. How long does an intelligent communicating civilization, which we have only become in the last few decades, exist before exhausting the resources of, or otherwise destroying the planet, or at least the civilization and the species which it created? So, astronomy times biology times sociology. If it's 6 billion years, then there are 9,000 intelligent civilizations in the galaxy. The nearest one is still 1,000 light years away. So it means they won't pick up our TV signals from the 1950s yet, because they're only 60 light years out there into space. And it means they don't necessarily come and visit us all the time, because 1,000 light years is a really long way, since a light year is 10 trillion kilometers. But it does mean they're all over the galaxy. Now, some people object. Well, if they're all over the galaxy, clearly they want to conquer the whole galaxy, and they should have been here already and taken over the Earth. I would submit that that's not true. You see, if the lifetime of the civilization is only 600 years, then there's one civilization, and it's us. So that's the choice we have, one civilization or thousands. And if there are thousands, what would that imply? It would imply that we're the youngest, dumbest civilization in the galaxy. Because we're 50 years old, and the average one is 3 million years old. So try to remember back 20 years before there was internet or cell phones. Okay. Now extrapolate 3 million years for me in technology. They're going to learn nothing from us. It's like an ant farm. Ant farms are really fun. The little ants crawl around and make tunnels. You don't learn a lot of nuclear physics from ants, but you can watch them. So there's 9,000 civilizations out there. The corollary is they're all vastly more advanced and more intelligent than we are. And perhaps what it implies is that they have gotten through this sociological bottleneck. Perhaps they don't decide that conquering the galaxy is in their interest. Perhaps manifest destiny, that we have to take control of everything we see, is not something their civilization any longer subscribes to. We live out here in the boondocks, as that little arrow is, of our galaxy, rotating around about once every 240 million years. There are 100 billion other stars in our galaxy, and more than 100 billion other planets. In the 17th century, the great Dutch polymath Christian Huygens, said this in responding to Galileo's discovery of the vast number of stars. How vast these orbits must be and how inconsiderable this earth, the theater upon which all our mighty designs, all our navigations, and all our wars are transacted is, when compared to them. And then he concluded as follows, with a message that would be worth repeating today. A very fit consideration and matter for reflection for those kings and princes who sacrificed the lives of so many people, only to flatter their ambitions of being masters of some pitiful corner of this small spot. You still have the earth over there? Yeah, very good. Imagine you're going to spend your life and 100,000 lives to take over 5% of it. Seems pretty pathetic, doesn't it? So the answer is here. N is, depending on your choice, of 600 years for intelligent civilization or 6 million years. In the first case, we're alone. In the second case, there's 9,000 civilizations, and we are the babies of the galaxy. It's important to remember I've only been talking about our Milky Way. It looks like on this picture, what's in that little square there? A galaxy of 100 billion stars. But of course, that galaxy has 100 billion stars too. It's just much farther away, so they're harder to see and they're fainter. It turns out that there are 10,340 more galaxies in this picture alone, each with 100 billion stars and a couple 100 billion planets. And it takes 17 million more pictures like this to cover the sky. 600 years ago, Nicholas of Cusa speculated on the possibility of life in the universe as follows. He supposed that on Earth there exists, in the form of men, animals, and plants, but let's suppose in a higher form, in the solar and stellar regions, there is life. Rather than think that so many stars and parts of the heavens are uninhabited, and that this Earth alone is peopled, and that with beings perhaps of an inferior type, he concluded, we will suppose that in every region there are inhabitants. Only if they're more intelligent than we. Good guess, Nicholas. Thank you very much. We have time for a couple of questions. If anyone has one, then shout them out. I have translation in my ears, so if this is Spanish, it's okay.
And can I
Can't see anything.
read?
Yes.
Is there a finding in your studies that can tell us?
El que quiera preguntas, aquí vamos a tener micrófonos y se los vamos a pasar los cojines, ¿ok? ¿Quién quiere hacer una pregunta? Tú, perdóname.
Sí, no te preocupes.
Me está poniendo la pila, Amazing top, Un aplauso, por favor.
Sí. No está tan pesada. Hola. Wow. Is there like an evidence in your findings that suggests how life came to be in the planet? I have read that there are some theories about the 12th planet of Zacharias Sitchin and Darwin's theory of evolution that life came from within, from the combination of elements that led to life. Is there something that can corroborate from where life comes from?
Yes, so for about 50 years, people have been trying to take in the laboratory test tubes and combine the raw materials that I said are everywhere and certainly were on the Earth, and spark them with lightning and things like that, and turn them into something. There has been not a lot of progress in that regard. You make lots of the organic molecules of which we're made, but you don't make something like life. Coming from the other direction, geneticists have reached a conclusion, having discovered more and more primitive organisms, way below bacteria on the evolutionary scale, called archaea, that possibly life began as an RNA molecule, not as a DNA molecule, which can be a much smaller molecule and much easier to produce. And so there are discussions in the literature of RNA life and the origin of RNA life, but no one's actually done it yet. No.
¿Alguien más?
No, la mala coordinación.
Una pregunta, ¿cuál es la definición aceptada generalmente de vida inteligente?
So I gave the definition of life which would apply to bacteria. The definition of intelligent life has been called into question by recent world events. But what I really mean is life that has developed technologically to the point where they could in principle, or even in practice, communicate over interstellar distances. Not travel over interstellar distances, just send radio waves over interstellar distances. And we've had that capability since we built the telescope in Puerto Rico, Arecibo, which can send out a signal, has sent out signals that are now coursing through space for thousands of light years and could be detected by an equally sophisticated or unsophisticated telescope. So when I say intelligence, I'm not talking about it in the usual sense, I'm talking about it in the technological sense that they have the ability to communicate across interstellar space and therefore give some signal that they exist.
Okay, we have another question.
Hola, buenos días. Mi pregunta es, ¿qué papel juega la paradoja de Fermi en explicarnos por qué todavía no hemos podido contactar con otras formas de vida inteligentes? No sé si me puede explicar un poquito de eso.
Right, so Fermi was not a fan of my argument. Fermi felt that if there were intelligent life distributed throughout the galaxy, then they would most likely have visited us, conquered us, colonized us, or whatever, and that we should see lots of signals from them and spaceships whizzing around and things like that. This was on the verge of World War II that he felt this, and of course there was a very strong notion that this is something innate in intelligence, that you want to conquer everything you can see. My argument is that a civilization that lives long enough to communicate over thousands of light years of space will have gotten over that impulse. So I prefer what I call the zoo hypothesis to the Fermi hypothesis. That is, we're in the zoo, and the intelligent civilizations are out there just watching to see if we're going to screw ourselves up. I'm happy to keep answering questions. But
We have another question there.
Hi,
That's it.
So this equation, by what you said, assumes that life has the same elements and I guess the same DNA structure that we have. Is there any adaptation of a formula that takes into account maybe living beings with 6 nucleotides instead of 4, or maybe based on different elements, extremophile living organisms that maybe takes it higher or down?
Right, this does not assume that DNA has 4 nucleotides or anything like that. It doesn't assume DNA even exists. It just assumes that chemistry is the same everywhere in the universe, and for that we have solid empirical evidence. The chemistry is the same. Now, what is life based on? Our life, of course, is all based on carbon. And that's because carbon is a unique of the 92 elements in being able to form bonds in the most number of ways. But for the universe, it's very important because carbon is the 4th most abundant element in the universe. It's hydrogen first, helium second, oxygen third, and oxygen, of course, is critical for life, and carbon. Now, you could use silicon or gallium or germanium or something like that, which also forms lots of bonds, although not as many as carbon. But they are 1/1,000,000th as common in the universe. So if we go with the simplest hypothesis, and that is we're going to use the most abundant building blocks, carbon and oxygen and nitrogen and calcium and things like that, then that's all the equation assumes. It doesn't assume anything about the exact structure or the hereditary nature or anything.
Just the last question.
Last question, yes.
My question is, can we theoretically basically travel, communicate faster than the speed of light? Well, that's it. That's the fastest.
The speed of light. You gotta listen to a talk coming up on Einstein. Or invite me back, 'cause I have a whole talk on that. Einstein's theory of relativity does not actually say that nothing can travel faster than the speed of light. But what it does say is what the implications of that are. And the implications are, for example, that the window in the front of this building would break before the kid that threw the rock through it was born. That is, it completely abolishes the notion of cause and effect. So physicists are comfortable saying that we don't believe anything travels faster than the speed of light because we sort of like cause and effect. And people have spent time looking for things. A colleague of mine, a colleague Gary Feinberg at Columbia, made up tachyons, which travel faster than light. They go backwards in time, they have negative energy, they can really mess up the world. People look for tachyons, we haven't found any tachyons. So all scientific knowledge is contingent. But the current best estimate we have is that no, nothing goes faster than the speed of light. Which doesn't mean you can't go anywhere, because if you go very close to the speed of light, time slows down for you to such an extent that you could live for thousands of years. There is now a project called Project Starshot, which is funded by one of these Russian billionaires, who's a little bit nuts, and what they want to do is send thousands of cell phone camera chips to Alpha Centauri, our nearest star, to get there in 20 years, which means they have to go about 20 or 30% the speed of light. And they have a plan for this. It's not going to work, but they have a plan for this. But it's an important moment in human intellectual history because it means people are actually thinking outside of our solar system. And it's not crazy to think in 50 years or 100 years or 1,000 years that we could do that with technology and then ultimately do it for ourselves if we don't mess it up. Thank you very much.